All right, hey, listen, welcome back, everybody. In the tents, we got Marcus. Marcus, say hi. All right, and today we're actually going to cover looking at what fits data better sometimes and what we could do. So let me share that screen with you, and let's go ahead and start this. All right, good. All right, so Marcus, go ahead and read what it says here. Read where it says guide to practice.
Guided practice, solving problems given functions fitted to data. Example 1. Chelsea has been tracking the fuel economy of her car. She has noticed that the fuel economy in miles per gallon seems to vary with the average speed of the car. Her findings are summarized in the following table.
Very good. Let me go ahead and start here. So basically, on the x-axis, we have average speed, and then on the y-axis, we have fuel economy. Okay, so this is X, this is Y. And Marcus, by looking at the data, what do you notice as you go higher in speed?
The number gets lower.
Yeah, number gets lower. And sometimes this is true of older cars. Newer cars, they design them to be attained to the speed. But like when you talk about an older car, before the speed limit on a lot of highways used to be 55 miles per hour. So sometimes they used to design the cars where sometimes the optimal speed was at 55. And anytime you went past that, it was like they would make the engine work harder in a sense because now you're going past the optimal speed. So in a sense, you're going to go faster, but you were using up more gas mileage because the way the transmission was geared. All right. So we have this data. So you're right, Marcus, about what you said. Now, hey, Marcus, why don't you go ahead and read the next part right here.
Create a scatter plot showing the relationship between speed and fuel economy. Which is a better estimate for the function that relates speed to fuel economy? Y equals 0.5x plus 50 or y equals 0.3x plus 46. What
Right.
value would you expect the fuel economy to reach when the average speed is 35 miles per hour?
All right, good. So Marcus, which one do you think is better?
I don't know. I haven't done any of the work.
I know, but what kind of equations are these? Because that's the same thing actually when my students reply say. They say, you know what, I don't know, I haven't done any of the, any of this stuff. Here you go. You see two equations? What kind of equations are these? So
Positive, or what do you want me to say?
they're actually linear. Yeah. Do you know why they're lines? Yeah. Do you know why they're lines? Why they're linear?
Because they have a x and y value.
Yeah, they have an x and y, but so do quadratics. Quadratics have an x and y and exponentials and everything else.
Oh, because it has no exponentials. It just has a slope, and that's all.
Yeah, it has a y-intercept. So let me go ahead and refix this in a bit. Got two things that are going for us. We have first y-intercept. Let's see. Let me bring this out. So we got the y-intercept right here. And then afterwards we have, so this is slope. M, this is the y-intercept. So if you're gonna graph these, one of them would get graphed like off axis. So I don't think it's that one, Marcus. It's probably the other one. You see the one starts at 46 and probably comes down. And it comes down by negative 0.3. So what does that look like, you know? Actually, negative 0.3, because that means it's gonna come down just 0.3 for every time we go over. But this is interesting. How much are we going? Oh, this thing is actually, okay, so you see where it says, now look at the graph. What's one thing that you notice about the graph that's different?
It's not a straight line.
Well, actually, you see how I put this dot right here? Let me see, okay. You see how I put that dot there? Yeah. Is that right for me to do?
No, because it's not on the graph, or?
Well, it's not 35. Yeah, in this case, that's wrong because it wouldn't. I could do that if L was at 0. So that's a mistake on my part. I can't do that. I'm starting at 35. Now, can I find out what the value should be at 35? Yeah,
Yeah,
because I should
you
be
just
able
plug it
to.
into the equation.
Yeah, exactly, right? I just plug it in. So if I do negative 0.3 times 35 plus 46, let me bring out, I have my phone, Marcus. Let me bring out the calculator on this thing. Or actually, you know what? Let me do it on, and you know what? I wonder if I'm screen sharing. Make sure I'm screen sharing. No, actually, I'm not. Let me hit share my screen, because then afterwards, one of the benefits I have is I could go over here and just type in that value. It's that way. Okay. I can type in that value in here. You're able to see my screen, right, Marcus? You see my Google Drive?
Yeah.
Yeah, right? Okay. So I should be able to type in negative 0.3 times 35, right?
Yeah.
46. That should tell me my answer is actually 35.5. Let's take a look at that. Let's look at 35.5. Now you see my screen, right?
Mhm.
Okay, good. All right. So that means that we're right here.
Yeah.
That means that we probably did well, and then afterwards to go down negative 0.3, which means that in this case we would now this is where we're jumping by 5. So now let's go see what the next data point is. Let's go ahead and do negative 0.3. Let's see. Negative 0.3 times 40. And it was plus 46, right?
Mm-hmm.
Yeah, so now it's at 34. So now let's see what that looks like. Okay, let's go back here. It's at 34, right?
Mm-hmm.
Yeah. So it's getting actually pretty close to. So that means that this, since it's linear, I'm able to guarantee a line like this. So we were right. Our initial impression, and it might have just been a guess actually, Marcus, because if I would have tried the other one might have been better. But I know that this is it, just because of the way the line is going. Does it make sense?
Yeah.
Yes, I know how that one's it. But you have to do that sometimes. And sometimes you do need to, like, if you know that you got the solution, great, love it, keep on going with it. But if not, like if you know that it may not be the right one and the other one might be better, there's some doubt. Try it out. Just try it. All right, good. So now let's do this next one, Marcus. All right. So Marcus, go ahead and read what it says here.
Graph the function on the coordinate plane. The function y equals negative 0.5x plus 50 is linear, so only 2 points are needed to draw the line. Evaluate the equation at 2 values of x, such as 40 and 50, and draw a line through these points on the scatter plot.
Okay, so it kind of took us through it. You notice how it's kind of like what we did. Remember how we plugged in values to see what they were at? Okay, so you notice how this one looks. So you notice how we were right. You know how this one doesn't match the data very well?
Yeah.
Yeah, so we were good. And now let's look at the next one. I wonder if they did the other one too. Actually, they did it for us. So we did all the work. So we knew that this one was the right one. They did the exact same thing on this one. And notice how this one's so much better.
Yeah.
Yeah,
It
right?
is a lot better.
It's a lot better, right? It fits the data a lot better. So if you had for some reason, now, what benefit do you have by converting the linear than doing the scatter plot in a way? Give me one benefit.
What is it? Wait, can you see the question again?
Yeah, what benefit do you get about creating this linear? This thing.
Oh, you could hypothesize or guess what each value is.
Yeah, you have the option now, because see, this one includes all values, all. Unless you put a restriction, it includes all of them. So that means that if for some reason you wanted to go past this graph, what is shown, and see something else, you have the power to do so much easier. because it's there. So that's one of the things that we do that all the time. We create things that kind of help us leverage things. Okay, let's look at the next one. All right. Okay, Marcus, read this question.
Identify which function comes closer to the data values. The function whose line comes closest to the data values is the better estimate for the data.
Yes.
Graph the function
Well,
y equals.
Marcus. So which one did we find out? Which one was it?
Oh, we found out it was y equals negative 0.3x.
Yeah, because it's the one that was closest to the data, right?
Yeah.
And then this last one just wants us to know. Actually, we did that. We found out this value specifically. Good. Let's see what else we got here. All right, good. Second example. All right, Marcus. So go ahead and read what it says here.
Example 2. The principal at Park High School records the total number of students each year. The following table shows the number of students for each of the last 8 years.
All right, so same thing. If you're going to discover a few things, that this is the x, that's the y-axis.
Hmm?
All right, and Marcus, what's one of the things you notice?
The numbers keep on going up with the x value.
Yeah. Is this normal sometimes?
Yeah,
Why?
because it's a linear thing still, and it's still positive.
It can be. Well, remember, population grows. Like if I know there at where I teach at Madison High School, they're building new homes. So sometimes there's more kids that go there to the school itself. And that's what happens to schools. There's more kids, it just grows. Okay. Now, they make a scatter plot, right? Now, this is kind of interesting. Look at this equation they gave us. What kind of equation is this, Marcus?
It's one without an x.
Oh, it has an x, but where's the x at?
Oh, it's the little, what is it called? Squaring number, exponent.
It's an exponential function. That's how it gets its name.
Yeah.
It's an exponential function because the x is where the exponent's at. And this is and don't feel, for those that are watching right now, note that all that's happening is this. If I made an x and y table based off this, Marcus, how would this look like? What would I start?
You would start at 1. Oh, 0.
I start 0, right? Okay, so 600, that x is 0 now. All right, so 600 times, what's 1.05 raised to the power of 0?
1.
Yeah. So you'll start at 600. And then when you do 1, let me erase some of the stuff. Now we're going to do 600 times, and this is a 1 now, right?
Mm-hmm.
I would do 600 times 1.05, right?
That
So,
would be 630 or something.
Yeah, exactly. Okay. Now, I want to go ahead and skip to like number 7. But let's do one in the middle. Let's do 5. Okay, so Marcus, what would it be at 5?
Okay, it would be
Actually, let me bring out my calculator so we all can see. Let's do it. Let me type in. Oh, but I have the calculator here. Good. Okay, so we do 600 times 1.05 raised to. It was power of
5.
5, right? Yeah, so 765. Okay. So let's go back here and let's put 765. And then let's do 8. Let's try it out and see what 8 is. So now, and the reason why I'm skipping is that I don't want to go through the whole, like if I pick up some points. Come on, clear up. Oh, it is clear. 600 times 1.05 raised to the power of.
Dad, you forgot the decimal.
Oh, you're right. That would have really affected me. That would be like, I'd be like, what happened? Okay, 886. All right, so now, so let's go to 886. Okay, so 886. So when I compare these numbers to the ones over here, so 600, 630, number 5 was 765, number 8 was 886. That's actually a pretty good percentage that I'm going on. Actually, I'm actually matching that up pretty well. You notice, oof. Does it make sense, Marcus? And you look at
Yeah.
that data compared to mine, it's actually matching up pretty good. Let's do that. Oh, it's because of my screen. So I was doing that at 5, we said it was 765, and then at 8 it was 886. So it's doing a pretty good job, actually. And I think that's exactly what the other examples are going to show. So let's go ahead and find out if that's what it does. Yeah, so it does the same thing we do. See how it calculates it? Table.
Yeah.
So table values, and they did the same thing we did. They jumped values. Notice that 1, 3, 5, 7, and look at the graph. So the graph does pretty good job with that as well. Let's see if there's anything else. And then they use the equation, because now when you have the use the equation, they could make an estimation of what year 9 was. And they'll say, oh, well, in year 9, you know, you should have 930 students. So they went to the conclusion that this is a good estimate. Okay, let's see. Okay, Marcus, let's read example 3. Read example 3.
Example 3. The weight of oranges vary. Maria wants to come up with a way to estimate the number of oranges given a weight. She weighs oranges and records the weights in the following grids.
Okay.
So,
And then look at the one she came up with. No, they ask you a question. She should use this one, 0.6. So now what's the difference here between these two equations?
one is just linear and the other one is exponential.
Mm-hmm. Yes. And let's see if I could bring up something that's pretty neat and helpful. It's Desmos. It's a Desmos calculator. And some of you have had the experience in the past of using Desmos. It's a really cool calculator. I love Desmos just because it makes it so easy. And one of my equations was 0.6x minus 1.5, right?
Mm-hmm.
And my other equation was 1.2 raised to the power of x minus 1. Okay. So interesting enough, they intersect at a certain, they intersect at 2 places. Take a look at Marcus at this equation. You see it?
Oh, yeah. They do.
Their places, right? Okay, but they start varying widely when they start hitting higher numbers. So let's see what numbers those are in comparison to what we're looking at. Okay, so now we're going to look at the x-axis. Let's look at 14. See if 14 is our biggest value right here? This one?
Yeah.
Our x value. Okay, so we're going to look at 14 on the graph itself. 14 is going to be here. Oh, I can't write on this. Okay, so when we look at 14, one of the values of 14 is at, let's see if I can zoom on it. One of the values is at 6.9, right? And the other one is at 11.8, somewhere around there. Okay, so which one is better, Marcus, now looking at it?
Probably the first one.
Actually, you're right. I agree with you. Yeah, the first one, especially looking at the data. And I'm imagining that's what these next slides are going to tell us. You know, like the first one's probably a better choice. So they show, you know, the plot. They probably graph. And they go ahead and start graphing some stuff, some of the points. So they show the same thing we show. And when they look at the data, they're saying the better fit is what we said.
Mhm.
See what I'm saying? Oops. I like, yeah, when we picked that. Good. And that kind of gives us, that's it. All right. Hey, so if anything, Marcus, what did you learn about today?
Okay, I learned that financial equation thing,
Uh-huh. And you learned
and that we could graph a line just by using dots on a scatter plot.
that you're able to, you be given data you can use, and the line, the biggest benefit is you could use to predict. Does it make sense? And then
Yeah.
certain lines work better for certain equations than others do. You know, and then some of
Of
them are
course.
related, you know, depending on how much data you're talking about. All right. All right, good. Okay.
Okay.
Hey, all right. So, hey, Marcus, love that you were with me. All right. Hey, go ahead and everybody tell everybody bye.
Bye.